This is a demonstration of the probabilistic time-space diagram. Each movement is modeled by a discrete queuing model. The queue length of the next time step xt plus 1 is calculated by adding the arrival a to the current queue length and subtracting the departure b. Uppercase xt is the queue length, while lowercase xtk is the probability mass function of the queue length distribution. X prime is the queue length after the arrivals but before the departure. The arrival probability at each time step is assumed to follow a Bernoulli distribution, and the departure is controlled by the traffic signal in a binary setting. The departure probability is calculated by the joint probability of x prime being larger than or equal to 1 and the probability of a green light. The queue length PMF can be updated recursively, where for each time interval there is an arrival step, which calculates a queue length distribution after the arrival, and a departure step to calculate x for the next time step. Note that the arrivals are factored in before the departures are removed, and the intermediate queue length distribution is denoted as x prime. We propose a probabilistic time-space diagram to project this discrete point queue model to the spatial temporal space so that its connection with vehicle trajectory data is established. To demonstrate the PTS diagram, start with an empty queue at time 0, meaning the probability of the queue length being 0 is 1. On the right side are Newellian coordinates parameterized by jam space headway and free flow speed. Vehicle trajectories can only travel on the edges of the grid. At time step 1, the probability of an arrival is 0.6. The red and blue arrows represent the transition probability to the queue length distribution after the arrival step, denoted as x prime. During the departure step for time 1, given a signal state of 0, blue and red arrows represent the transition probabilities to the final queue length distributions. The point queue representation can then be projected to the PTS diagram. The arrival probability is shown in light blue. The transparency of this line reflects the probability value of 0.6. The purple line depicts the probability of the queue length being 1, which is 0.6. In this case, the PTS diagram essentially shows that, with probability 0.6, there is a new vehicle arrival that will stop at the first location. At time step 2, the probability of an arrival is 0.5. Once again, we calculate new queue length distribution after the arrival step. After the departure step for time 2, given that the signal state is still 0, we have the resulting queue length distributions. The queuing process can be projected to the PTS diagram again. The arrival probability of 0.5 is shown in light blue. In order to find the probability that this arrival will continue on and move to the first stop location, we take the product of the probability that there is no existing queue and the probability of an arrival to get 0.2. For the stop state at the end of time 2, the probability that a vehicle stops at the second location is 0.3. The probability that a vehicle stops at the first location is 0.8, which is the sum of the probability that the queue length is larger than or equal to 1. We then update the PTS diagram for an arrival probability of 0.4. Notice now that the signal state is 1, so there is a departure whose probability can be calculated by taking the product of the probability that there is a queue of some length and the signal state. The PTS diagram is now updated for a fourth time step. In summary, we can project the point queue representation to a spatial temporal space and represent the probability of a vehicle traveling on each edge in the probabilistic time-space diagram. Therefore, the PTS diagram directly shows the spatial-temporal distribution of vehicle trajectories. On this page, we will show how the PTS diagram can build the connection between the queuing model and the observed vehicle trajectories. From the previous diagram, take the third timestamp as an example. The current arrival probability is 0.4, and the queue length distribution at t equals 2 is given in the table. Let the penetration rate phi be 20%. Given these conditions, there are 4 different possible observations. First, we observe no trajectory. This could happen if there is no arrival or a new arrival that is not observed. Second, we observe a trajectory that passes directly through the intersection. This could happen if we observe a new arrival and the previous queue length x2 equals 0. Next, an observed trajectory stops at a queue length of 2, which could happen if we observed a new arrival and the previous queue length x2 equals 1. Finally, we observe a trajectory stopped at a queue of 3. This could happen if we observe a new arrival when the previous queue length x2 equals 2. The probabilities of each of these events happening are reported below the respective diagrams. Now we will briefly discuss how to utilize the PTS model to estimate the traffic state and its parameters. First, we explore the probabilistic graphical model to describe the relationship between different parameters and random variables. We start with stationary parameters that include the arrival rate and penetration rate. Given the arrival rate AT, we get an arrival A. The traffic signal state is denoted as S. Both of these influence the queue length X. The average delay can be measured directly from the queue length distributions. Together, the arrivals, queue lengths, and average delay comprise the overall traffic state. From the vehicle trajectory data, we get an observation composed of an observed arrival, an observed queue length, and an observed average delay. Traffic state and parameter estimation estimates the traffic parameters and the traffic state given the observation y. In traffic parameter estimations, we use the method of moments estimator to estimate the penetration rate and arrival rate by matching the average delay between the model and the measurement. Finally, the traffic state can be estimated through a Bayesian estimation where we find the posterior distribution of the overall traffic state given the existing observations and parameters.